Good afternoon. We are starting the afternoon session. We'd like to introduce Mr. Samuel Williams. He is invited as a guest speaker for the 7th Ruby World Conference. He is very active as a multi-language programmer, exploring the new frontier of software engineering, computer vision, augmented reality, programming languages. He has obtained a master's degree, and he works as a freelance consultant, and he enjoys solving conundrum. And the future dream for him is to complete the picture drawing robot going around the world and create artworks. He's going to talk about asynchronous Ruby.
Hello, my name is Samuel, and I'm here today to talk about asynchronous Ruby. What makes Ruby a great language? When I first considered giving this talk, I thought about that. So naturally, I asked on Twitter, and here are the results. Syntax was the most important, followed by semantics, libraries, and finally scalability. Someone also wanted to vote for maths. We all love maths so much. Thank you for inventing Ruby, and thank you to everyone who contributes to making it a great language. So let us consider these different aspects of Ruby. Syntax is very important and the most visible part of the language. It affects how we read and write code. Semantics, how the language works and fits together, affects how we think about the code. Libraries provide the scaffolding by which we make bigger, more complex applications. They expand what we can do with a single line of code. But what about scalability? What does it affect? In order to understand how scalability affects the language, we should first define what it is. At its core, scalability is about the efficiency of your program. If you double the number of hardware resources, your program can do twice as much work in the same time. Ideally, it's a proportional improvement. Let us consider the different forms of asynchronous execution that allow us to build asynchronous programs. Within a typical computer, we can run multiple processes. And within those processes, we can run one or more threads of execution. Processes and threads execute simultaneously, which means that our tasks can execute at the same time. We refer to this as parallelism. Within one thread, we can use an event loop to interleave multiple tasks. This becomes especially relevant when our application is waiting on user or network input. An event loop requires some way to manage the state of each task and switch between them. We can do this using fibers. The event loop cooperatively schedules all the tasks on a single thread. When the current task performs a blocking operation, it yields back to the event loop, which allows another fiber to execute. We refer to this as concurrency. Why is scalability important? There are many technical reasons, but one big issue is climate change. Efficient, scalable systems are good for the planet. Less computers are required for the same work. The technology sector is responsible for 2% of global carbon emissions. I hope that my effort to improve Ruby's efficiency can be a useful contribution towards reducing climate change. So coming back to our original question, what does scalability affect? Actually, scalability affects all areas of a language. How does scalability impact syntax? In order to build more scalable systems, many languages expand their syntax, including things like callbacks, which are sometimes wrapped in promises, which have necessitated the introduction of the async await keywords to help manage the flow control issues created by callbacks. What about language semantics? We may change the behavior of blocking and non-blocking operations, synchronization primitives to handle shared mutable state, or making shared objects immutable to avoid data corruption. How does scalability impact libraries? If libraries make too many assumptions about parallelism and concurrency, they may cause strange problems when used together. The most important question being, is this code thread safe? Thread safety means that code behaves correctly even when executed by multiple threads in parallel. Google recently instrumented the Linux source code to detect thread safety issues. I quote, "Google is uncovering hundreds of race conditions within the Linux kernel." I think it's safe to assume that Linux kernel developers are very skilled, and yet there are still many problems. So what hope is there for us mere mortals? Let's consider the current situation. Is Ruby thread safe? Let's talk about money. Money is a gem used for handling monetary amounts and currencies. It has 23 million downloads. It uses a global mutable hash table to store exchange rates. We use this to convert between currencies. Let's take a look at the implementation. Here is the rate store, which is used for storing exchange rates. Here is the method which adds an exchange rate. The hash table update is wrapped in a lock by the transaction method. So far, this looks okay. Here is the code that implements the locking. When we enter this method for the first time, the block is correctly synchronized, but it also sets in-transaction to true. If another thread enters the same code path at the same time, because in-transaction is true, strangely, we skip locking the mutex, and so we potentially have unsynchronized reads and writes. Let's take a look at how this can go wrong. Thread 1 correctly acquires the mutex. Then thread 2 enters the same code, but it bypasses the mutex because in-transaction is true. The result is we may have unsynchronized reads and writes. I made a simple test case using 1,000 threads to add 100 random exchange rates each. Here is Ruby 2.6. We added 100,000 exchange rates in total. And at the end of the test, the store correctly recorded all of them. It looks okay. The global VM lock sometimes hides threading issues. Here is JRuby, which does not have a GVL. Again, we added 100,000 exchange rates, but at the end of this test, the store only contains 18. This is because the underlying data structure was corrupted. Let's talk about Nokogiri. Nokogiri is a gem used for parsing HTML and related formats. It has 260 million downloads. Nokogiri can use CSS queries to select elements in an HTML document. Internally, the CSS query is converted to an XPath query, which is an expensive operation. So a shared global cache is used to avoid repeating these conversions. Here is the function for updating the cache. It uses a mutex to synchronize access to the cache, which is good. But this block of code switches the cache on and off. It's mutable global state, and there is no locking, which is bad. Let's take a look at how this can go wrong. Cache on starts off as true. Thread 1 saves the current value of cache on and then sets it to false. Thread 2 sets the value of cache on, saves the value of cache on, and then also sets it to false. Thread 1 finishes its work and restores the value of cache on to true. Then thread 2 does the same, but what value does it write to cache on? True or false? It ends up writing false, and from this point on, caching is permanently disabled within Nokogiri, which can impact performance. Let's talk about Faraday. Faraday is an HTTP client which uses a stack of middleware to handle things like redirection, serialization, and timeouts. It has 183 million downloads. Here is the code for managing the middleware. This mutex is lazily initialized. Here is what lazy initialization looks like. It's not an atomic operation as you might assume. It's several operations which happen sequentially. This Ruby code actually executes more like this. Let's see how this can go wrong. Thread 1 checks to see if middleware mutex is defined, and in parallel, thread 2 does the same check. They both return false, so both threads attempt to create a monitor and update the instance variable. As you can imagine, this doesn't work out too well. Sometimes it works correctly. Other times, the lazy initialization is ended by multiple threads. Let's talk about RAC. RAC is the bridge which connects web applications with web servers. It has 322 million downloads. Sessions are a global mutable state which is used to store whether the user is logged in or if they are an admin user. Here is the session management code. This method, commit session, is responsible for allocating a session ID and persisting the session to a global pool. This delete session method deletes the current session and returns an unused session ID, but importantly, it doesn't reserve it. Later on, write session uses that session ID and saves the session state into a global hash table. Let's see how this can go wrong. Thread 1 deletes the current session and generates a new session ID. Thread 2 generates the same session ID. Then thread 1 writes the session state to this new session ID. And thread 2 overwrites this state with its data. It's possible that the user's logins would be switched. Fortunately, this particular situation is unlikely to happen in real production applications. Let's talk about Redis. The Redis gem is used for accessing the Redis server and has 117 million downloads. Redis has a per-thread queue of commands which it uses to implement pipelining. Here is the client implementation. All functions use this synchronize method to ensure only one thread can access the connection at a time. Well, almost all functions. The queue method doesn't have any locking around adding the item to the underlying hash table. Additionally, the hash table has a default constructor which can turn reads into writes. So this operation, with no locking, can potentially read and write to a shared hash table, and it's even encouraged to be used from different threads. Let's see how this can go wrong. Thread 1 and 2 are both adding items to the queue. Thread 1 is computing the hash table bucket to insert the item, while thread 2 triggers the hash table to be resized, so the index computation in thread 1 is now invalid. In some cases, I've been told this can even crash Ruby. Let's talk about Ruby. Ruby is okay, you already know what Ruby is, I hope. This is a backtrace from one of my programs. It reports a deadlock, but my code is not doing any kind of locking. It turns out it's actually a bug in the Ruby interpreter. The Ruby interpreter held a lock in a situation where it was possible that the user code may also try to acquire the same lock. You cannot acquire a lock twice. It causes a deadlock. The solution is to ensure that the mutex is unlocked if there is any chance of calling user code, but it is a very difficult issue to solve in general. So let me again pose the question, is Ruby thread safe? This has a mutex, it's thread safe. Unfortunately, source code analysis reveals too many mistakes and incorrect assumptions. So, what is the solution? Node.js. Okay, let's draw some inspiration from Node.js. It uses a single-threaded, event-driven architecture. This avoids thread safety issues because there are no threads. To scale up, you run one instance per processor. Here is an example showing how to fetch a web page using event-driven callbacks. First, we make a request to the specified URL and provide a callback for when the response is received. We create a buffer for the response body and add a callback to accumulate it. Finally, we specify a callback for when the response is finished, which prints out how many times Ruby was mentioned in the Google search results. Also, we need to have a callback for handling errors. I would argue it's not so easy to write. It's not so easy to read, and thus it's not easy to understand. So what about async await? Surely this is going to solve all the problems. Here is the same example, but we need to wrap the callbacks in a promise. Here is the main logic where we request the page. We need to explicitly define the code, which is going to be asynchronous using the async keyword. If we change a method to be asynchronous, all the code that uses it must be updated. Then we must know to add the await keyword here. Is this actually an improvement? What about Ruby? Here is the same example in Ruby. Here we make a request and it returns the body. Done. It's so simple. But it's not so scalable. Because this is a blocking operation, it is easy to saturate many threads. Once that happens, you cannot do any more work. What about fibers? Here is the same example, but using asynchronous fibers. We need to start our task using an async block. We instantiate the internet, and then the remainder of this code is largely the same as before. It's still simple, but it's also scalable. This code can be executed today using the async gem for Ruby. Its core abstraction is the asynchronous task, which provides fiber-based concurrency. Tasks execute synchronously from top to bottom, so no special keywords or changes to program logic is required. Blocking operations yield control back to the event loop, which schedules other tasks until the operation can continue. The core of async is less than 1,000 lines of code with good unit test coverage. Lately, I've been looking into async as one of my projects would really benefit from non-blocking I/O. It's really beautifully designed. Janko Moronic on the general design of async. Async has a growing ecosystem of scalable components, including support for Postgres, Redis, HTTP, and WebSockets. There is also a pull request to support the event loop within Ruby on a per-thread basis. This will allow us to expand the approach to existing code with minimal changes. I was also recently awarded funding to continue working on this, which I am very grateful for. If you would like to try it out for yourself, there is an online tutorial. In addition to async, I developed Falcon. It's a pure Ruby web application server. It supports HTTP1, HTTP2 with zero configuration. This gives you a modern localhost development environment. It can also be used in production without Nginx. It uses one fiber per request for concurrency, and it uses a hybrid multi-process, multi-thread model for parallelism, so we can support CRuby, JRuby, and Truffle Ruby. Is it scalable? Well, like anything, it depends on how you use it. But various micro benchmarks show that it can perform very well, especially when there are non-blocking operations like database queries. Async is the right model because web applications are almost always I/O bound. The Ruby web ecosystem is really lacking in scalability. Example, WebSockets on Perma. Async unlocks the next tier of scalability in the most Ruby-like way possible. Brian Powell on migrating from Perma to Falcon. Does it work with Rails? Yes, it's Rack compatible. There is also an interactive online tutorial for Falcon. What are the next steps? It depends on you. The community. Please try it out and give me feedback. The businesses. Please consider supporting this important work. You can also use GitHub sponsors, which is exciting. Thank you.
Thank you very much, Samuel. Now we would like to entertain questions from the floor. Any questions? The person has already raised a hand. Yes, the person in the front line. Thank you. Thank you very much for your talk. My question is the following. In your talk, you talked about the thread safety. And in talking about that thread safety, you talked about Nokogiri, Faraday, Rack, Radius, and Ruby. These are the things you raised, and there are many downloads for them. This is what you said. Nokogiri, Faraday, and others. In this topic, why did you select Nokogiri, Faraday, Ruby, Racks? What is the selection criteria?
When I first approached this problem, I thought it's meaningful for people to see gems that they will be using. So I downloaded the Postgres dump from Ruby Gems, and I ordered it by download count, and I selected the top 10,000 gems, and I have a folder on my desktop with 10,000 gems in it. Then I made some source code analysis tools to analyze the code for potential thread safety issues, and I went through it from top to bottom. So actually, I have a question for everyone else. Does anyone here not use a gem? Like, does anyone here doesn't use any of the gems I mentioned? Anyone? Right, so everyone has potentially got some effect from like these thread safety issues. So my goal was to relate to people's existing use case.
はい。はい。
大丈夫？
ありがとうございます。
Thank you very much. Thank you very much.
ありがとうございます。ご質問いただきました。
Thank you very much for the question. Any other questions? Yes, the person in the center.
Thread safety in your talk, and you also mentioned fiber. And what's your idea about fiber safety? Like, is it like existing anyway, or there's nothing like fiber safety? What's your idea?
When you combine threads and fibers together, you can have thread safety issues become fiber safety issues. For example, if you acquire a lock and then your fiber will yield, then another task resumes and tries to acquire the same lock, it can lead to a deadlock, and that is unexpected from the user's point of view. So I think the simple answer is threads create these problems. The way that people use mutex, they acquire them and hold them for too long, and so it leads to performance problems. So I think to answer your question, if you can isolate fibers, then there are still synchronization-related issues, but they don't tend to yield like crashing your program. So the class of errors is greatly reduced. But when you combine fibers with threads, then you introduce like a new kind of class of errors that can occur as well. So it's quite tricky. So I think my goal is to, with CRuby, when you use Falcon with CRuby, you use multi-process. So you only have, Falcon does not have threads on CRuby. So some of those issues can be mitigated. But yeah, I think if you look to what Koichi proposed with guilds, I think the goal is to isolate user code from threads because it's just too difficult. And then the nature of fiber safety issues is greatly reduced.
Thank you.
You're welcome.
はい、ありがとうございました。はい、どうぞ。
Thank you very much. The person who is sitting next to this, there is a hand raised. No, it's not the questions. Are there any other questions? No? Oh, yes, please.
I have heard that fiber is not so fast enough. By maybe Koichi Sasada by Koichi Sasada said so, and I think about fiber performance of fiber is very important for Falcon and async gem. And do you have any idea that fiber improvement?
In my talk at RubyConf Taiwan, I did a talk called The Journey to 1 Million, where I covered several improvements to the implementation of fibers in Ruby. The most notable ones are we wrote native assembly code for the coroutine transfer operations. And the other most interesting one is we bulk allocate the stacks for the coroutines and we cache them. So when we allocate, like say, 10,000 fibers, we only call the operating system like logbase to 10,000 times, which minimize the overhead of communicating with the operating system. Whereas if you look at, like, say, p-threads, you will need to do one operating system call per thread. So comparatively speaking, fibers are potentially much more efficient if they're implemented correctly. So all of that work is coming out in Ruby 2.7, and there were micro benchmarks showing sort of like 100 times improvement or something like this. And also the memory usage is improved as well. So those problems are solvable, and I think the vast majority of them have been solved.
Thank you so much.
You're welcome.
ありがとうございました。
Thank you very much. Any other questions? Yes, please. Will you please wait for the microphone to come?
Could you explain, if you take a library or application written with threads in mind, how difficult is it to convert to working asynchronously? I mean, probably depends on the library, but based on your experience, what do you think for the average library?
So there are a couple of people who are really excited by async, and we have this discussion. When you look at the implementation of the libraries for users' consumption, you often have two parts. The part which is dealing purely with the interface of the library and what it's talking to, like say a database layer would be talking to a database server. And that's kind of a protocol-specific thing. And then you have, on top of that, the nature of asynchronicity, so whether there's parallelism or concurrency. And those two things can be split. We've proven that in a lot of the implementation. We have protocol HTTP1 and async HTTP, protocol Redis and async Redis. And so there's a layered approach to building these out where protocol Redis could actually be reused in a context where threads are the form of asynchronicity that you want. So coming back to your question, the problem is that a lot of libraries, they blur those lines between what it is to deal with the protocol or the thing you're trying to interface with and the model of concurrency you use to deal with it. And that makes it very tricky in some situations. So active record is a tricky one. We've had some success, but we have to monkey patch the connection pool handling. Whereas with SQL, your own gem, it was a little bit simpler because it abstracts that out more cleanly and makes it easy to go in there and make the required changes to support it. So it's kind of a case by case, but I think in conclusion, like to really answer your question, it just ends up being easy to rewrite stuff if it's just a huge mishmash. If there's layering violations, it can be very hard to solve. And if people aren't enthusiastic about it, making pull requests is quite depressing. So yeah, thank you.
ありがとうございました。
Thank you very much. Now it is time to close this presentation. Thank you very much, Samuel, for your wonderful presentation. If you have any questions, please come to Samuel individually and ask questions. Samuel Williams wearing a very nice blue boots. Sorry, beautiful ruby color boots. Thank you.
Come and see me in the Hackspace.
だから、はい。
I have more t-shirts, motto. So come to the Hackspace and you can have more t-shirts.
昨日のレセプションの時にもです。
Well, yesterday, the reception as well, he gave that T-shirt as the present. We appreciate he bringing. So he was carrying a bag, and out of the bag, he took out a chocolate and lots of things. I thought it was a Santa Claus in disguise. So thank you very much.